voy a hacer el compartir. Estamos en el primero que estamos en vivo, ¿ok? Puedes partir.
¿Okay? Puedo comenzar, ¿cierto?
Puedes comenzar, Felipe.
Muy bien. Muy bien. Hola a todas y a todos. Les doy la más cordial bienvenida a nuestro quinto webinar de este año 2023. Queremos dar un cordial saludo a toda nuestra comunidad UC y también a nuestra comunidad extra UC y profesionales que nos acompañan desde todo Chile. Quisiera también darles un anuncio importante, es que este webinar se realiza una vez por mes, por lo que estaremos intentando también cubrir distintos temas y cumpliendo las expectativas de los temas que ustedes nos proponen. Esta vez contaremos el webinar de hoy con un amigo profesional, un terapista respiratorio destacado internacionalmente, que nos hablará de la evaluación al lado de la cama del paciente, ¿cierto? La evaluación clínica del reclutamiento pulmonar durante en pacientes con ventilación mecánica. Sin embargo, antes de presentarles a nuestro invitado de hoy, quería darles un par de anuncios sobre nuestra carrera y las distintas actividades que nosotros realizamos. En primer lugar, quiero mencionarles que pueden seguir nuestra carrera en todas nuestras redes sociales, Facebook, Instagram, y en el link de nuestra web, ya que tenemos un equipo muy activo de personas trabajando para entregarles toda la información que desarrollamos en el día a día. Además, quiero comentarles que tenemos una página web muy completa, donde encontrarán parte de los webinars que se han hecho anteriormente y puedan revisitarlos cuando ustedes lo requieran de manera gratuita. Además, quisiera contarles que en nuestro canal de YouTube pueden también encontrar todos los webinars que hemos realizado de manera gratis, por lo que también les recomiendo suscribirse a nuestro canal. Y, por ejemplo, ya pueden ver, ya está ahí registrado el último webinar del mes pasado, que ya tiene aproximadamente más de 600 visitas. Una información importante es que en el link que ustedes están viendo y están siendo conectados en YouTube, pueden encontrar un chat donde pueden dejar todas las preguntas que tengan sobre la presentación de Tomás, y así yo poder realizarlas al final de la presentación. Así que pueden ir dejando sus comentarios en la medida que vaya viendo o les surgen las preguntas durante la presentación. Otro detalle muy relevante es que pueden ingresar a través del código QR o la página web menti.com, ingresando ese código, para votar por algún tema, ¿cierto?, o tópico que les gustaría que abordáramos en los siguientes webinars. De esa manera podemos contactar a los distintos invitados y expertos para que nos puedan hablar de temas variados relacionados a la kinesiología. Y por último, quisiera mencionarles que nuestra educación continua en la universidad es muy activa este año y que están disponibles diversos cursos y diplomados en los cuales ustedes se pueden inscribir. Así que los invito cordialmente a revisar la página web de nuestra carrera y de la educación continua UC para que puedan inscribirse si así lo estiman conveniente. Sin más preámbulo, ahora quiero presentarles al colega, terapista respiratorio certificado, Thomas Piraino. Él es, como les decía, un terapista respiratorio registrado, canadiense, el cual sirve como profesor, ¿cierto?, del Departamento de Anestesia y Cuidados Críticos de la Universidad de McMaster. Es reconocido internacionalmente por estar presente en más de 50 conferencias internacionales, participación en investigaciones, editoriales, libros. Aparte es quien maneja el blog del Centro de Excelencia de Ventilación Mecánica del profesor Laurent Rochard, es miembro del Consejo Asesor de la revista Respiratory Care y ha ganado varios premios y reconocimientos sobre sus contribuciones a los cuidados respiratorios. Así que, sin más preámbulo, dejo con ustedes a Thomas Piraino. Thank you, Tom. You are very welcome. Thanks for being here.
Thank you very much for having me. Can you see my slides okay?
Yes, we can see it right now.
Excellent. So I'm going to be discussing bedside assessment of lung recruitment during mechanical ventilation. This is not the same as a recruitment maneuver. What I'm going to be discussing is how to assess the potential for recruitment so we know whether or not patients will be able to tolerate higher levels of PEEP or recruitment type maneuvers with them. So I have a few conflict of interests, nothing related to this talk directly. I do have speaker and consultation fees from Draeger, Fisher and Paykel, Philips, and Aerogen. I will discuss a electrical impedance tomography device that is made by Draeger. They are not supporting me for this talk, so I'm simply using it. I will have some images of the device simply because I've used it clinically since 2013. So it's been 10 years I've used the device, and it's the only device I've had at my disposal, so most of my pictures are with that device. And I just want to say quickly a thank you to Felipe, who we are now, it's 6 years since we became friends and colleagues working with Dr. Laurent Burchard. And we've traveled to AARC Congress together a number of times now, both virtually online during COVID and now twice in person. And we've had many dinners together with other friends and colleagues. There's Dr. Lu Chen, who I will mention his talk later. He's right here. Dr. Tai Pham. We have Dr. Ewan Gallagher, Dr. Eddie Fan, just a whole bunch of friendly faces that we both really enjoy working with. And I spent a few days alone in the lab. Everyone was away except for me, Felipe, and Cesar. And we decided to try to teach me some Spanish. So hopefully this comes through.
Después de 3 días, ya domino el español.
Now, it's been 5 years. I'm no longer dominating Spanish. Okay. So the learning objectives for this presentation will be to describe a bedside method for assessing recruitability that can be performed with any ventilator, and to describe how electrical impedance tomography, which is a certain technology, how this can also be used to assess recruitability at the bedside. And I'll discuss some recent publications that we have out. So again, as I mentioned, I'm going to be discussing the potential for recruitment. And this is not a new concept. Dr. Gattinoni published this paper in New England Journal of Medicine in 2006, talking about the potential for recruiting a lung or the potentially recruitable lung. And in this example, what they did, you can see in the top right here, they took a patient, an ARDS patient on a PEEP of 5 or a CPAP of 5, and then they increased to a CPAP of 45 centimeters of water. This was experimental. It was not something they do typically clinically. This was in the CT scan. And for this patient up here, you can see that there's some collapsed areas at a CPAP of 5, and essentially the same number of collapsed areas on the CPAP of 45 centimeters of water. So this person has very low potential for recruitment. The higher percentage for recruitment down here, you can see a patient with a lot of collapse and consolidation here in the lung. When the area of the lung is opened up with 45 centimeters of water, there's still some areas of consolidation that likely will not open at this pressure, but there's a number of areas that I've highlighted here in yellow that were recruited. So this is the volume of lung that has been recruited. Now, the question also lies is that does the recruitment of this area here that is yellow, does this perhaps over-distend the area that was already opened? And this is something that EIT can help assess, and I'll get to that in just a moment. But essentially, we're looking for the amount of lung that is available for opening. Now, why should we be interested in the recruited volume or recruitment potential? Well, the most recent guidelines we have, this is just one of, not a guideline, I should say, sorry, the systematic reviews that we have on high versus lower PEEP. This is one that's more recent, and you should be able to scan the QR code if you want, and the title and the authors are there. This was published, I believe, in 2017. And I just highlighted some important points here where they say, we suggest higher PEEP not be used among unselected patients with ARDS of any severity. In other words, randomly assigning to use higher levels of PEEP all the time on patients with ARDS is not acceptable. They suggest higher PEEP strategies for selected patients deemed to have a greater amount of potentially recruitable lung. We would discourage the use of high PEEP for patients without potential for lung recruitment with high PEEP. Now, nowhere in this article do they discuss the absolute way in which you should assess this recruitment potential. There's another article in the Lancet that was published during COVID-19 very early on in the pandemic, giving some suggestions. And again, they also mentioned this PEEP here, and the potential course of action over here says individualized PEEP. It says consider PEEP in patients with evidence of higher potential for recruitment. Now, it does say as suggested by CT scan or the recruitment to inflation index. Now, this is supposed to say the recruitment to inflation ratio, which is what it's referred to in the paper. And I'll discuss that maneuver in just a moment. And it's also saying, or with patients who have a body habitus or clinical exam that suggests high pleural pressures are likely. This is, of course, related to patients that have morbid obesity. Now, just to quickly describe why we are interested in the amount of volume that a lung is recruited with when we increase PEEP. And it comes down to the amount of strain that we are placing on the patient's lungs. So strain refers to the deformation or the change in shape of a structure compared to its resting condition. So for the lungs, the resting condition, if you take the lungs and you put 0 of PEEP on a lung, then the end expiratory lung volume would equal their FRC. So their FRC is their baseline structure, their baseline volume of lung. When PEEP is added, it always increases end expiratory lung volume. Anytime you increase PEEP, you increase the volume in the lung. Now, this may or may not open up previously collapsed units, and this also complicates the strict interpretation of lung strain, and I'll explain why. If you increased PEEP and there was absolutely no recruitment of the lung, the end expiratory lung volume that is added to the system when you increase PEEP will go into the numerator, which would increase the strain on the lung. If you had a lung that had 100% recruitment, so every volume that increased when you increase PEEP, if all of it went to recruit and open up the lung, then the end expiratory lung volume would be in the denominator, which would actually reduce lung strain. Now, of course, it's never all or nothing. It is likely a compromise in every situation. When we increase PEEP, essentially there will be areas of the lung that will recruit, and I've mentioned it here as the change or the recruited volume. And so the end expiratory lung volume that we add when we increase PEEP, and we can estimate how much volume we're adding when we increase PEEP. I'll explain how in just a moment. It's very easy math. But when you increase PEEP, that end expiratory lung volume, it will go into the numerator, but anything that's recruited will likely be beneficial. So it may balance some of the effects of adding PEEP. And estimating the increase in lung volume is something that can be done at the bedside. One of the methods is the slow flow inflation maneuver, the pressure volume curve. This is a compliance curve when you use very low flow. So the recommended is less than 9 liters per minute of flow is ideal. Typically, I prefer 5 liters per minute of flow to use for these slow flow inflations. The reason why you go slow is because you want a pressure volume curve. You want this compliance curve to represent the elastic forces of the lung. So you don't want resistive forces. So by going very slowly into the lungs, you reduce or eliminate any of the resistive pressures that may be present in this pressure volume curve. So this is how we should be doing it. Now, when you do this, if you look on the right-hand side, you can see that there is a slope here. And this slope is just pressure and volume, which if you take volume and pressure, this is what compliance is. So compliance is 35 milliliters per centimeters of water. Now, this is an example of compliance. I'm guessing it's around that when I look at this image, but I'm going to give mathematical example using 35 mils per centimeter of water. So if you increase PEEP, so this is on a PEEP of 5 and we're ventilating this patient. Now, if I were to take the PEEP from 5 and increase it to 15, based on the compliance curve, I can estimate how much end expiratory lung volume would be added simply by using this pressure volume curve. So if I increase the PEEP from 5 to 15, I'm going to gain about 350 mils in this example here. So if I increase by 350 mils, how I got that was quite simple. If the compliance is 35 mils per centimeter of water, and I increase by 10, I just multiply 35 mils per centimeter water by 10 to get 350 mils. So this is the expected. Now, if I increase PEEP to 15 and the compliance of the lung was exactly the same and there was no recruited volume. Now you could have the same similar compliance, but have recruited lung, but let's assume that I don't recruit anything and the compliance is the same, then I can estimate where my end expiratory lung volume happens. Now, what if when I increased my PEEP, the graph shifted? So let's say I do a multiple PV curve. So I have it on PEEP of 5, I increase PEEP to 15, it does another PV curve immediately. If it doesn't follow the exact same line, if the baseline shifts, this is the recruited volume. So this is one bedside method for using or for measuring recruited volume. I don't know one clinician that does this clinically at the bedside. It involves multiple PV curves. The patient has to be sedated and paralyzed, which for the next thing I'm going to tell you, they should be also sedated and possibly paralyzed. There should be zero effort. So that's not different, but this requires a slow flow inflation curve, which means a very, very slow respiratory rate. It would be probably close to 5 breaths per minute if you were to do this properly. So everything will be extremely reduced. You have to be careful of acidosis, et cetera. If you make a mistake, you'd have to start over again. So it's not typically done clinically at the bedside, except for research purposes. But this is one of the ways you could determine how much volume was recruited. Now, the bedside method that I'm going to describe, which is the RI ratio, just so you know, the study was a validation study to see whether or not doing a simple bedside maneuver can estimate or determine, again, we're looking at whether or not it can estimate with an acceptable degree, acceptable limits here, and whether or not it correlated very well, which it did, to this bedside method of multiple pressure volume curves. So the method I'm about to show you is highly correlated. It was a validation study to assure that this method we're doing at the bedside is telling us what we hope it's telling us. Now, the threshold for recruitment that I'll discuss later is something that they had to choose, but it really was the median value for all of the patients. But I'll explain why it's not always the best to use a specific cutoff value. But here's the maneuver briefly described. If we go back to this multiple PV curve here, what we're essentially doing is we're increasing the PEEP to 15. So rather than starting down here, we're starting on a PEEP of 15. So let's say I'm this patient here, I'm on a PEEP of 15. And we're going to reduce the respiratory rate to ensure that there is no auto PEEP. I'm going to show you a video of me doing this maneuver on an actual ventilator as well. But let's say we're on a PEEP of 15. We're going to reduce the PEEP down to 5 on the machine, and then we're going to wait for that breath to release. When that breath releases from PEEP of 15 down to PEEP of 5, you will have not only your exhaled tidal volume that you were ventilating here at a PEEP of 15, but you're going to release all of the end expiratory lung volume. So if you look at the graph over here, when I drop from PEEP of 15 to 5, I'm going to lose all of this volume in that single breath. Then I'm going to be ventilating with my tidal volume just as I was normally, so it's going to go back to normal. But that very first breath, when you drop the PEEP, is going to release all that end expiratory lung volume. So what this maneuver is doing, it's basically saying, if I measure this release here, this huge release right here, I know what's predicted based on the compliance of the lung. Again, 15 to 5. If I know my compliance is 35 mils per centimeter of water, I know that I'm going to release 350 mils, but anything else that I release is considered recruited volume. So it's essentially a way of getting this recruited volume backwards rather than starting low and doing multiple PV curves. You start at the top and you release. And when you're on the PEEP of 5, you measure the plateau pressure, which gives you the compliance can be calculated, and then the estimate can be referred to, et cetera. So this sounds like a lot of math. When I show you it on the ventilator, you're going to see it's probably simpler than my explanation. And I've actually created an online calculator that you just plug in the values and it will do all the calculations for you. But what is the recruitment to inflation ratio? Let me go back to the slide quickly. This recruited volume is mils, it's in milliliters. And the change in pressure is the change in PEEP that we made. So we dropped from PEEP of 15 down to 5. So it's 143 mils per change in pressure, 10 centimeters of water. It's 14.3. This is just rounded up, or sorry, rounded down here. So 14 mils per centimeter of water. The recruitment to inflation ratio takes that compliance, that recruited compliance, which is the recruited volume divided by the change in pressure. It takes that, what I just told you, and divides it by the compliance of the respiratory system at low PEEP. That's it. It takes those two compliance values and it gives you a ratio, which is called the recruitment to inflation ratio. Now, in the paper, they suggest that greater than or equal to 0.5 indicates an increased recruitment potential. Now, the important thing to understand is that if your patient is 0.49 and you do another patient and they're 0.5, you wouldn't call one patient recruitable and the other patient not recruitable. It's a spectrum. You have to understand that the higher the number is, the more recruitable the patient is. The lower the number, the less recruitable they are. Now, of course, in this study, they just have the median was 0.5, which is why they have the threshold of recruiters and non-recruiters. So I'm going to now demonstrate on a ventilator how we would do this maneuver. I'm going to use the numbers from this example in my calculator on the next slide. You'll see the numbers in the calculator. So this is how it's performed. This is a servo eye ventilator. So the things we want to pay attention to and put in the calculator are the set tidal volume, the exhaled tidal volume, which I'll look at it again right at the beginning or right before the breath drops. There's the plateau pressure. I have the ventilator set with a 0.2 second pause during volume assist control, which gives plateau pressure in real time. Otherwise, you'd have to do a brief inspiratory pause if you didn't do that. So now I'm going to reduce my rate first to ensure that there is no auto PEEP. This gives a long time for exhalation. There will be no auto PEEP caused by a high respiratory rate. Now I'm going to go in and drop my PEEP from 15 down to 5. And as soon as you do that, you have to pay very close attention here. There's the breath right before the release is 398, but then watch. All the volume is going to be released from the end expiratory lung volume, and it's going to register right there. It is 818. So when you drop the PEEP, you lose that end expiratory lung volume that the PEEP was giving. Now this is going to go right back to typical numbers. It's going to level itself off here. All I've done now is I'm looking at the plateau here. It's 17 centimeters of water. At the low PEEP it was. Now that I'm back on PEEP of 15, you see it increases back to 26. So the things that we wanted are high PEEP, low PEEP, 15 to 5. The set tidal volume was 400. The tidal volume exhaled at high PEEP was 398 right before the next breath, which released. The released breath was 818, and the plateau pressure at low PEEP was 17. I click calculate. My recruitment to inflation ratio is 0.26. There is no very, very low, or you could say no recruitment potential in this example, which that example was actually a test lung. So it makes sense the test lung was not recruitable. And this calculator can be found at rtmaven.com. I'll mention it again in case you need to write it down later. Now, there is one caveat. There's one tricky thing with the recruitment to inflation ratio, and that is if the patient has something called airway closure, then this can affect the values if you don't compensate for it by putting in the calculator. And if you notice, there's actually a box up here to put in airway opening pressure if you discover it. So what is airway opening pressure or airway closure? When you do slow flow inflation curves, again, pressure volume curves, there's this point here which for decades has been called the lower inflection point. It is clearly a lower point and there is an inflection there. But when the inflection is quite significant, what some authors like Dr. Chen are considering is perhaps we've misinterpreted this historically as always being a point of recruitment. This is actually, in this example, it's the point of the airways opening. And how does he know this? This red line is the pressure volume curve of the ventilator circuit with the end occluded. So it's just the compliance of the circuit, which obviously is very low, which is why this is very low here. This pressure volume curve line is very low because it's just the circuit. And if you notice, the pressure volume curve of the patient is following along the circuit until this point at which it then opens up. So there is no volume going into the lungs until that point. And at that point, it's actually a linear curve. So this patient would have interesting compliance measurements that would be inaccurate based on the fact that there's airway closures. So we should assess this airway closure phenomenon. Again, rather than doing a slow flow inflation pressure volume curve, if you don't have pressure volume curves on your ventilator, what you can do is use a pressure time curve. And I'll just explain why this is important. Again, if we use this example here, let's say the low PEEP is 8, and then we want to do a recruitment to inflation ratio, or we increased PEEP of 18. So 18 to 8 should be a difference of 10. But if the patient has airway closure and they don't open until this point right here, then the actual delta pressure in this example is 3.2 centimeters of water. So rather than there being a change of pressure in 10, it's actually 3.2. So every calculation I did before where I said the change in pressure was 10, the increase in PEEP was 10, we've increased PEEP by 10 here, but it's actually only affecting the lungs this much, 3.2 centimeters of water. So if we know the AOP, then the equation just changes. It's PEEP high minus AOP rather than the low PEEP. And here's an example of how to measure the airway closure on a patient. Again, on this ventilator, I don't have a slow flow inflation maneuver for pressure volume curve. So I'm going to use a mode of ventilation, which you can use volume assist control. On this ventilator, I'm actually going to switch to SIMV simply because I can make all the adjustments and then hit previous mode. Now this patient is on pressure control, so I could have switched to volume assist control and then switched back going to previous mode. But a lot of our patients are managed with volume assist control. So I got into a habit of using SIMV simply because many ventilators allow you to quickly push a button to go back to the previous mode. That's the only reason why I use SIMV for this, but you can use volume assist control for what I'm about to show you because I'm using SIMV with volume assist control. This patient is sedated and paralyzed, so there's no effort. So I'm just using a mode that I can then, if you look down here, there's a button that says previous mode. That's why I'm using a different mode to do this. So I'm putting my respiratory rate down to 5. The tidal volume I'm just setting to close to 6 mils per kilo. Now this ventilator, you can't adjust the flow, so you have to adjust the I time. But if you look up here, I'm adjusting the I time to get a flow of 5 liters per minute, right? Because I want to do a slow flow inflation. I'm going to put the PEEP. You can put it down to 5. Some people will go down to ZEEP, but I won't clinically go below 5 in this patient. I'm going to hit accept. The PEEP is going to drop down to 5 centimeters of water. And then once it delivers the breath, it's going to deliver it very slowly with 5 liters per minute of flow. And watch the pressure here. See how the pressure increased? And then there's this angle here where then it changes shape and goes linear. So now I'm just hitting that button, previous mode, because I'm just going to scroll back just a second. When it starts, I hit this button up here called save. It's just like taking a screenshot. On this ventilator, it records a video that's 30 seconds long, but if you have a screenshot, it would do the same. You want to take a screenshot. Then I go back to the previous mode. So while I'm looking at the pressure waveform and assessing it, I don't want the patient to be on a rate of 5. So I quickly go back to the mode. So let me just skip ahead here. So once it's done its recording, I'm going to hit the menu and go to my recorded values. And I'm going to move my cursor along here. You can see this inflection here. This is airway opening pressure right here. So I put my cursor here. See, it's around 16 or 17 centimeters of water. So this patient, if they were on a PEEP less than 16, it's just when we deliver volume, it first has to overcome the airway opening pressure, then it will ventilate the lungs. So this is the patient that should not be on a PEEP less than 16. Doing the recruitment to inflation ratio doesn't mean the PEEP has to be at 16, but this would be the minimum value of PEEP that would be required for this patient. Now, this patient was on a PEEP of 18 because we had already done the maneuver. We already knew this, and I just wanted to record it. So we were checking again for the airway closure, and I recorded the video this time. Now, this is not that patient's numbers. These are the previous numbers we did before. And if you recall, if I just quickly scroll back, the recruitment to inflation ratio on my previous example was 0.26. Okay. Now, if we discovered that a patient, those same numbers, had an airway opening pressure of 9, it changes the recruitment to inflation ratio because the pressure, although we went from 15 to 5, it actually went from 15 down to 9. So the change was 6 centimeters of water. So when you plug this in, it will rework the calculations so that you have an accurate recruitment to inflation ratio. Okay, so let's talk about some exciting technology. It's no longer new. I'm used to saying this is new technology, but I've been using this technology for 10 years now. It's new for some people. Some people have never even seen this device because it's an expensive device. If you do work in a hospital that has one in South America, you may, and Felipe, maybe you can give me a thumbs up. Is the Timpel more popular down in there? Like in Chile, is it? Do you see Timpel or do you see both? Both? Okay, that's good. It's good to have competition. I like that there's two different devices. I've used them both. They both have things I like and things I don't like. So I'm impartial. But let's talk about recruitment potential using electrical impedance tomography. This QR code up here, I'll put at the end of the slide. It's just a review that I wrote on electrical impedance tomography published in Respiratory Care that just describes sort of, it's just an introductory on like how to understand and interpret EIT. So this is the screen on the Palma Vista, which is the device by Drager. The other device is by Timpel, the other one that I'm referring to. But this one here is the Palma Vista. It has ventilation. So although you can't see it in the screenshot, this is a dynamic image, which means as the ventilator delivers a breath, every time this goes up and down, this image is actually changing, showing you where volume is going throughout the lung. So this is like a slice, like a CT slice, and this is not a talk on electrical impedance tomography, so I won't spend too much time explaining this, but just know that it gives us where it shows us where volume is going into the lung. Now, how can we use this for assessing end expiratory lung volume? So this has been used in a number of studies now, where if we want to determine the increase in end expiratory lung volume, we can measure the change in end expiratory lung impedance. So this is just ventilating a patient over time as we increase PEEP. So I can put a cursor here and a cursor over here, and I can see that the increase in end expiratory lung volume in this example was about 4.8 times the height of this. Now this is different than this example down here, but clinically, if we're doing research, we would measure the end expiratory lung impedance here using an offline analysis. The end expiratory lung impedance here, we would just subtract so we know the difference of it. And then we multiply it by the tidal volume being delivered on the ventilator and the tidal impedance as a ratio to convert it to volume. Sounds very complicated, but it's actually extremely easy to use if you understand how to use this device and its offline analyses. In terms of using EIT to estimate recruitment volume, the only study I've seen out there comparing it to the method, the flow-derived method, as I mentioned earlier, is this study in animals, where it's a nice linear relationship. The R-squared value is acceptable. It's not as high as the recruitment to inflation ratio. The level of agreement is not as tight as the recruitment to inflation ratio. But again, this is animals. I don't know how this would perform. So anyone who's interested in research, this is something that you could do possibly rather than in animals, you could do it in humans. And just to show you the results from the paper on the recruitment to inflation ratio, you can see the R-squared is higher, 0.798, and the level of agreement here is much nicer, in my opinion. So one of the issues I have as a clinician and my understanding of EIT is that if I just look at the increase in end expiratory lung volume, that's great, but I don't know, I can assess where this volume is going, but I don't know the impact on the function of the lung that it is having. What do I mean by this? Here's two patients that if you look at this is the increase in end expiratory lung impedance. This is just a factor increase. This is just an arbitrary number essentially, but it's an increase of 1 in the ventral regions, and an increase in 0.63 in the dorsal regions. This patient has very similar 1.07 and 0.66. If I were to look at that, I would not understand if there was a significant difference between each of these patients' response to PEEP. However, the nice thing about electrical impedance tomography is it gives you other types of analyses you can do, like assessing the % increase in compliance when you increase PEEP. So this patient here, when we increase PEEP, this is PEEP of 16 and PEEP of 25, you can see that there's a 35% increase in compliance and only a 2% loss of compliance. This is a very recruitable patient. This patient had a similar increase in end expiratory lung volume, but it didn't go into the areas that I want it to go in, despite it saying 0.66. This little area here is not significant improvement in compliance. In fact, there's a 24% loss of compliance and only a 4% increase in compliance. So two extremely different patients in terms of their functional response to PEEP. And this is important because just looking at the volume, we don't know how it affects the function of the lung. And they're two very different patients here. However, right now, there's currently no standard for what level of percent changes is considered significant. There's also, I have not found studies using this specific tool on this specific EIT device to assess recruitment potential. This is clearly a change in compliance. The other method that is used quite often is something that's referred to as the Costa approach, simply because he was the author that first published this approach. But essentially, this compares compliance loss at low PEEP and compliance loss at high PEEP to give you an idea of collapse and overdistension. And again, there's no standard percent as to what is considered a large amount of collapse or not. But in this paper, which we just recently published online, I was just looking to see, Felipe, if you were on this one, but you were not part of this. So you were already gone back to Chile. So I apologize you weren't on there with us, but I'm glad you weren't stuck in the COVID-19 rooms with me. Maybe you were back in Chile, but not in Toronto. So for this study, they took tertiles of collapse to distinguish patients with low recruitability, medium recruitability, and high recruitability. I want to point out that these tertiles are based on their data. It's not it's not saying that you are a low recruiter if you fall into this category. They just separated it by low, medium, and high recruiters. They could have also done low and high and just done right down the middle, but I think it's very smart that we did low, medium, and high recruitability with this. But you can see, again, using the same technology with EIT, they would increase the PEEP to 24, and we would do a slow decremental PEEP trial from 24 down to 6. In the low recruiters, you can see there's a significant amount of overdistension that occurs at higher levels of PEEP. And when you decrease PEEP from 16, you start to have collapse, but there's not a lot of collapse because there wasn't much lung that was recruiting. In the medium recruiters, you can see there's less overdistension at higher PEEP, and there's more collapse at low PEEP. And for the high recruiters, there's a significant amount of collapse at low PEEP. And again, there's always overdistension that occurs at PEEPs of 24 when you're comparing it to PEEP of 6. Now, this is different than my example here. I'm just comparing PEEP of 16 to 30. It's not comparing two extreme PEEP levels. Here, it's comparing 24 down to 6. So there's clearly some overdistension up here, and there's a significant amount of collapse with this. So what did we find with this paper? Again, we're looking at the recruitment potential. This is specifically in COVID-19 patients. This is an ongoing study. This is just a first analysis of it. And we looked at, for patients so we looked at the crossing point. The crossing point means the point at which overdistension and collapse are the most balanced. Okay, so we looked at this graph and said, okay, so this would be EIT-derived optimal PEEP. The optimal PEEP with EIT is one that balances overdistension and collapse. So they choose the crossing point here, the crossing point here, and the crossing point here. One very common method of choosing PEEP is by looking at the best compliance, because you assume if the lung is the most compliant, then it must be the most happy state of the lung at that PEEP level. When they compared the crossing points between the EIT and the PEEP level with the highest compliance, you can see the numbers are somewhat similar, but again, these are the median values. I'm going to show you the graph that shows the same patient on one PEEP and another, and you can see that, let me just go ahead one. There's very little agreement between the two methods for each individual patient. So if it was the same PEEP at the crossing point and the same PEEP during compliance, these would all be straight lines across, because it would be choosing the same PEEP for each method, but it wasn't choosing the same PEEP per patient. So although these medians are similar, you can see every patient had a different response. So it has it down here for the low recruiters. 6 patients ended up, it was a higher PEEP for the optimal compliance. Over here, 21% for optimal compliance had a decrease in PEEP compared to the crossing point. So most of the patients, to get the highest compliance, required a lower PEEP. And this is actually consistent with some of the data that we've seen over the years. Here's an example. The patient with the highest compliance is this PEEP level right here. And you can see the significant level of collapse that has occurred here. Here, the highest compliance point is about here. It's close to the crossing point, but just so you know, from one patient to the next, you might see one that it seems to match the crossing point, at least relatively close, and others where it's off by almost 3 or 4 centimeters of water. And in fact, they found that the range of change was either -4 to +6 in terms of the difference in PEEP that would be applied for an individual patient. Now, for the level of collapse, the change in collapse for low recruiters, it was a median of 16, and there's the range, the interquartile range, 32 for medium recruiters, and then 46% at high recruitability. Again, that's the median collapse at the lowest level of PEEP. They did compare it to the RI ratio, and I mentioned earlier that having an absolute cutoff of 0.5 was something that they had to do for the publication because it's nice to know that there's a threshold, so you have an idea of like, oh, it's 0.7, they must be a recruiter, or it's 0.3. But in this example, they're low recruiters. Again, they define low recruitability by simply separating their data into 3 categories, right? Tertiles of recruitment. So the RI ratio for the low recruiters was 0.59, which in that paper would have been a recruiter, but it's on the cusp. And then the medium recruiters were significantly higher than that. And the high recruiters, again, both of these values were significantly higher than the low recruitable patients. They also did the RI ratio EIT based. Again, it correlates. It does the same thing in terms of it's higher for patients with higher recruitability. But this is not commonly performed, RI ratio with EIT. I figure if you have EIT, you can probably just use other methods to determine recruitment potential. One of them being the Costa approach, where you can see the degree of collapse that occurs when you get to your low PEEP level. So I do have quite a bit of time for questions. And I put some QR codes here to bring up some of the articles. The first one is just the RI ratio paper, the initial validation paper of looking at that method for assessing the recruited volume and then using the RI ratio to classify recruitment potential for a patient. And then there's the introduction article that I wrote on EIT. If you're interested in other techniques, there's the another paper by Thomas Piraino and colleagues that also sort of describes EIT and its use. And if you go to our blog, comv.blog or .ca, .blog is easy to remember. The most recent post is actually discussing this paper here, which is published. There's a link to the paper. It's open access, actually. So even if you don't have access to the Blue Journal, you can get it. But the recent blog post is a summary of this paper. So if you want to start with the summary, you can check out our blog, and you can find me all over social media.
Thank you so much, Tom, for this clear and very nice presentation. We really appreciate having you here. So thank you so much. We have a couple of questions here, so I'm going to read some of them. Mm-hmm. So first one is related to the AOP and RA ratio. So it says if you have any AOP, and then is this related to lower compliance? And if we assume that if we remove that delta pressure from the equation of RA ratio, is that we are overestimating the potential for lung recruitment? Something like that?
So if we remove AOP, then the RI ratio would decrease because it does affect compliance both of the recruited lung and of the main lung. The issue is that the delta pressure is not what we think, but it does affect both your compliance measurements and your recruited compliance measurements. So it's possible that your RI ratio may not change by much. I believe there are some scenarios that I plugged in numbers and the RI ratio didn't change much because it affects both values. It affects the compliance measurements of the baby lung, which is the denominator, and also the numerator, which is the recruited compliance. So AOP doesn't, I'd have to put in a bunch of different scenarios, but essentially it does it can change your value, and it's extremely important just for compliance alone. So forget RI ratio. If you are assessing your patient and measuring compliance, and your compliance seems very poor, if you assess for AOP and increase the PEEP above AOP, your plateau pressure should not change very much. So your compliance would improve because you're just, again, the pressure you're increasing, you're just getting past the point of airway closure. So once you do that, your respiratory system compliance will drastically improve, depending on the degree of AOP. If it's only 3 centimeters of water higher than where you set your clinical PEEP, you're not going to see a magical change in compliance. But if you're on PEEP of 5 and you have horrible compliance and you increase PEEP, actually a good example is obese patients. Many obese patients may have this phenomenon of airway closure at low levels of PEEP. They have such high pleural pressures at baseline. They just functionally very different. And these patients, as you increase PEEP, you see improvements in compliance. And some of it may just be because the pressure is not even touching the airways or the alveoli until you get past airway opening pressure. I don't know if I answered the question, but it typically will affect the AOP. But I do believe there are some numbers you can choose where because the change in pressure affects both, it could possibly balance out. I believe it happened to me once, and I was very confused as to how the number didn't change when I added AOP.
No, thank you so much. One of the questions related to the RA ratio is that the number, right? And you clearly mentioned that 0.5 number criteria was the median of the data, right? That's what I, as far as I understood. So the question for you is now, what do you think about this number? You clearly mentioned that it's better thing in a range of value, but clinically sometimes we observe 0.8, 0.9, and to me, in my experience, it's really hard to get 0.2, 0.1. So what do you think about this value and this criteria in terms of the RI ratio?
So I do think the threshold is a difficult one to stick by, I would say. I have seen patients with very low RI ratio, but it's also very obvious when you increase PEEP that they're going to be one of those patients. So essentially, when you increase PEEP to 15 and the compliance becomes horrible, your driving pressure increases drastically, your hemodynamic status changes on your patient. Those are patients that you try to do the maneuver very quickly and you end up finding out that they're not recruitable, but it kind of makes sense. So I think the utility of it might be in repeated measurements to know whether or not your patient is no longer getting benefit from the PEEP level that they're on compared to a lower PEEP level. So trending the number over time, I think, is helpful. If you were to separate your patients for recruiter versus non-recruiter, I think the utility of having the value is that if it is high, if it's 0.8 or if it's 1.2, this is a patient that I'm probably going to use a higher PEEP strategy, meaning something probably higher than 12 centimeters of water. 12 to 16 is probably where I would start. If it's lower, even 0.5, 0.6, I probably would use a moderate PEEP level. 10 to 12, the problem with the RI ratio, and a question I get asked a lot is that, so if it's a number, where do you set your PEEP? And that hasn't been established yet. We don't know where you should set your PEEP. We just know that they probably benefit from a higher PEEP. And it basically tells you whether or not the PEEP, if you're doing 15 to 5, it tells you that on a PEEP of 15, there's likely some benefit if your RI ratio is high. If it's questionable, then maybe 15 is not optimal. Maybe 12 is best.
No, absolutely. So, and one of the issues that we had a few months ago is that in some patients that they have very low compliance, we wanted to assess this RI ratio, and it was really difficult to get into the PEEP of 15. Yep. So
that's what I was just saying. When you increase that PEEP, if your driving pressure gets horrible, you can't do it. Yeah.
Exactly. So my question is there any safety parameters that you observe or in order to do not harm patient, right? Is any plateau pressure that you use as a safety limit or something like that?
Yeah, I believe so. In Toronto, where I used to work at St. Michael's and where you were doing research with us as well, they use what's called a registry form, where every patient who has a PF ratio less than 200 gets a full workup, esophageal pressure, recruitment to inflation ratio, you name it. And if I recall correctly, they do have an upper limit of 35 centimeters of water for plateau when increasing PEEP to 15, which would be a driving pressure of 20. If it's higher than 35, you abort. If it's not, you move forward, because the entire maneuver will take you, like, it's 5 to 10 minutes. A patient can tolerate a driving pressure of 20 for, the few minutes it takes to do the maneuver. But anything higher than 35, I believe, is their cutoff, saying to abort the maneuver and not to perform it.
Have you done this from PEEP 12 to PEEP 2, let's say, keeping this delta of 10 centimeters of water?
I've done that before. I've done that before.
Yeah, sure.
You could, again, technically, you could choose any PEEP you want, but the paper, you could do, 12 to 8. I'm not saying you should. I'm saying if you did that, it would still give you numbers when you plug them into the calculator. But the study used a drop in 10 centimeters of water to have a significant expiratory driving pressure, right? So when you go from PEEP of 15 down to 5, you have a significant release of pressure. Because PEEP is a resistive pressure on the ventilator, so you reduce that resistive pressure, you have a good release. So even if you have AOP, you want to, let's say your AOP is 8, you still would set your ventilator 15 to 5 and then put 8 in the calculator, because you want that very minimal expiratory resistance. So you would set from the ventilator. So you set the PEEP at 5, even if you know your AOP is 8. But yeah, getting the PEEP to 15 can be challenging. I probably would use that upper threshold of 35 centimeters of water as a maximum plateau pressure, keeping in mind that some ARDS studies, like the high-low PEEP studies, like the LOVES trial, allowed plateaus of 40. I'm not suggesting we do that. I'm just saying, they allowed it as part of their protocol. So you allowing 35 centimeters of water of a plateau for 5 to 10 minutes it takes you to get these measurements, I think is okay.
So there's one interesting question from the audience saying that any advice, clinical advice to measure some lung recruitment potential in patients under pressure control or during assisted mode ventilation? Is anything that we can estimate in these kind of patients?
So most of the measurements, I shouldn't say most, all of the measurements that are available in the intensive care unit for measuring changes in end expiratory lung volume generally require a very cooperative patient, mostly because it involves either slow flow inflation maneuvers, that if the patient's breathing, it's affecting the ventilator. I don't know of any that have been utilized or validated against a standard method where the patient is passive. Having said that, studies have reported things like improvement in compliance, which you could possibly say would relate to some recruitment, like using EIT in spontaneous breathing patients. So there's reports of using EIT in spontaneous breathing patients where they see an improvement in the distribution of ventilation. Could you call that recruitment? Sure. Do we have threshold values and stuff like that? No, but definitely you could use. So with EIT, you can use any mode you want because you're seeing where the air is going. So it's kind of doesn't matter what the ventilator is doing. You can see whether or not volume is increasing to an area, but also if the compliance is improving to that area alone. But compliance itself doesn't always indicate the best or safest place to put your PEEP. But it generally will indicate that you've recruited a lung. I mean, I don't think anyone would argue that if your compliance goes from 20 centimeters or mils per centimeter water to 35 mils per centimeter water, that you didn't either recruit something or you clearly had some airway closure that you've now overcome. But where you set your PEEP is questionable. But you could assess recruitment simply by looking at improvements in compliance. You likely would have an improvement in gas exchange that would accommodate that. But would you label it as that? I don't know. Mm-hmm. What about you, Felipe? What do you think? Would you essentially look at, if the patient's compliance drastically improves, that there's either you've increased over AOP, like maybe you've gotten over some airway closure, Or you may have opened up a lung that is ventilating the whole patient better.
Wow, no, I don't know, right? It is when you
We
you
answer
have a
that question
patient
with
like
solid.
yeah, and then you are doing some spontaneous effort, it completely changes everything, right?
Yes. Yeah.
You can recruit some areas, you have more heterogeneity in some parts of the lung, so it's
Yeah.
really
The
hard to
issue is,
establish.
yeah, I think the issue you would face is that you would have to ensure that effort has not changed.
Yeah, because it can
Like if you
change
want to
in
say
various
compliance has,
from
yeah.
yeah,
If you want to say compliance has changed, you have to guarantee that effort has not changed, because the effort will change as per equation of motion. It will change your volume. So therefore,
exactly.
and it may alter pressure. It may not alter pressure if you're in a pressure mode, but it will change volume, which will change your compliance, but it might have nothing to do with lung recruitment and everything to do with the change in effort. So
Yeah, but
yeah.
it can be some. We can do some simulations. It's interesting, right?
Yeah.
Trying to control different variables.
Yeah.
Let's see.
I think, I mean, it always is intriguing when compliance improves in a patient who's breathing spontaneously. You want to assume that, oh, we must have opened up a lung. But unless you can visually see that and assure that it's not because the patient increased their effort, because yes, they increased their compliance by effort, but maybe that's not a good or safe level of effort, right? If the effort is now excessive, Felipe is a very smart person with effort and the potential damage to the diaphragm. So you would have to ensure that any improvements you think are happening aren't because the patient's now working their diaphragm too much. So this is where it gets very complicated, which is why most papers on recruitment potential, measuring end expiratory lung volume, they all have to do with passive patients because it's the most accurate. And then you take out that component of patient effort that can change everything.
Yeah, no, very interesting. So Tom, there is one question related to EIT here. So so if you observe some de-recruitment in the EIT, is that always associated with the over-distension? Is really observing de-recruitment, or is just like we're observing that it's not improving? You know what I mean? It's like we're observing really de-recruitment, like a loss of some aeration of the lung, or it's just like it's not improving and it's not changing after some maneuvers.
I may not understand the question. Is it essentially like you're using EIT to monitor and you view that there's a change in the distribution of ventilation? So the question is whether or not this would be considered over distension or collapse. Is that?
Yeah, something like that.
So to answer that question, you really need to look specifically at the patient and the mode that they're on. Okay. Why I say that is, let's say someone's on volume assist control. So you are guaranteeing 6 mils per kilo of predicted body weight going to that patient. If you walk by and you see that the distribution of ventilation is no longer going into the dorsal lung regions, you know that 6 mils per kilo is going into the ventral lung regions if that's what's happening. That likely would lead to overdistension. Okay, so you're only ventilating one area with a tidal volume that is supposed to be for all the lungs. With pressure control, if I walked by and I saw de-recruitment or very little ventilation occurring in the dorsal lung regions, let me just bring up an image of EIT. So if I walk by and I see very little distribution down here on pressure control compared to the last time I saw them, likely what you're going to see is there's going to be a decrease in tidal volume because it's pressure control. It's not guaranteeing a volume. If you've lost distribution of ventilation to a large area of the lung, your tidal volume is probably lower than it was the last time you saw them where their lung was more open. So would that be over distension? It would depend on how much volume is still going into the lung and whether or not it's injurious to that area. But I would be more concerned. So if I saw that pattern, let me see if I can find an example of the pattern here. Yeah, so if I walk by and I saw this like very little blue, and this is actually the wrong image, but okay, let's say I saw this. When I came by the first time, I saw something that was much more homogeneous. Now I see this. If it was volume assist control, I would be more concerned immediately because I know the same tidal volume is going into a smaller space and likely my driving pressure will be higher. If it was pressure control, your driving pressure probably hasn't changed. Your volume is dropped and you're on pressure control, so the pressure's not changing. So it might look the same. The white just means that that's where most of the ventilation is going. Some people think this is over distension. That's not what it's telling you. It just means white is the maximum point of inflation. You want the white to be evenly distributed everywhere. When it's all in one spot, this could be 200 mils, which may not over distend the lung, but if most of it's occurring here, it's white. So you just have to understand the colors of your device. I know the Timpel has slightly different colors. You just need to know what these colors are meaning, because technically over distension, if your lung's not ventilating, it should be very dark. So, but if all you're ventilating is the ventral regions, it's going to be the brightest color. Now here's an example of increasing PEEP. See here, this patient, as we increase PEEP, you see how it's quite bright here, and then it's losing a lot of the brightness here. At this point, this would be over distension, even though it's not white. I would consider this area to likely be starting to feel over distension because it's not ventilating the same. And then you could say, well, is this over distension? Well, most of the volume is going to one area, so you could call that possibly over distending that area. This is why looking at the colors, you can't call, oh, it's white, it's over distended, or oh, it's decreased, it's over distension, because decrease here is not over distension. Decrease up here likely is. So if it's decreased in the ventral region, it's likely over distension. In this patient, if I saw this clinically, I would reduce my PEEP. If I saw this patient, I probably would try to increase PEEP if they tolerate it.
Totally agree. So, Tom, well, thank you. Thank you so much for this presentation. I think we had a really nice webinar. We really appreciate having you here. Thank you. Thank you so much. It was really nice to see you again, and hopefully see you in person in Chile. You can visit us whenever you want.
I hope to visit soon.
Thank you so much, Tom. Bye, my friend.
Thank you very much. Bye-bye.
Muchas gracias a todos por la conexión a este webinar. Agradecemos a Tom por esta presentación genial y explicativa que nos realizó. Y los dejo invitados a todos para que se puedan unir a nuestro próximo webinar del mes siguiente, para que sigamos conectando y compartiendo distintos temas relacionados a la kinesiología. Así que me despido. Muchas gracias por todo. Un abrazo y nos vemos en la próxima.